I was at the beach with my nephew last summer, and you know that feeling you get. You're trying to build a sandcastle, and the dry sand just slips through your fingers.
Right. You can't get any height.
None at all. But then you add just a little water, and
Oh.
suddenly you're building these vertical walls that seem to defy gravity.
That transformation, that's what we're talking about today. It's a fantastic real-world example of material physics. We're going to do a deep dive into the mechanics behind it all.
So we're looking at the forces between tiny grains of sand to see how they let us build these, sometimes massive structures.
Exactly. We'll get into the friction, the surface tension, and really understand the recipe for that perfect sandcastle.
Okay, so let's start with the basics. Dry sand. Why is it so useless for building?
Well, the key term here is that it's a cohesionless material. Basically, the sand grains only interact by pushing on each other.
Just friction and physical contact.
That's it. So they can handle being compressed, but you can't pull on them. That's why you get that shallow slope, the angle of repose. It's usually only about 30, maybe 35 degrees.
But the second you add water, that whole equation changes. You suddenly have a pulling force.
You do. A huge one. Even a tiny bit of water creates what scientists call a capillary bridge between two grains of sand.
And that's just the water clinging between them.
Right. And because of water's surface tension, that little bridge tries to shrink, and in doing so, it pulls the two grains of sand tightly together. It's like a microscopic glue.
And the strength of that glue is, it's kind of unbelievable, right? I was reading a single one of those bridges can support a force hundreds of times the weight of a grain of sand.
Up to 400 times in some cases. It's incredibly powerful.
So if it's that strong, why do so many of my sandcastles just collapse?
Because it's all about precision. The best sandcastles exist in what's called the pendular regime. That's where you have these perfect isolated little water bridges acting like super glue.
And this is where my intuition it completely fails me.
Right.
Because the research says the ideal amount of water is what? It's shockingly low.
It is. It's about 1% water by volume.
1%. I'm definitely using way more than that. I'm probably pouring in 10, 15%.
And that's what most people do. But it brings up the big question. Why is less actually more here?
Yeah, why?
Once you go past that 1% mark, those perfect little bridges start to merge. They overlap. You move into a different phase, the funicular regime.
So you're going from tiny dots of superglue to just a puddle.
Exactly. And when the bridges merge, you lose the extreme curvature of the water's surface. And it's that curvature that generates the strong pulling force.
Yeah.
So you're actually diluting the strength. Too much more and you just have a slurry.
Wow. Finding that precise optimal point where the physics just works perfectly, it really makes you think about how progress in almost any field is just about optimization.
It really is.
And speaking of optimizing things, this deep dive is brought to you by Silk. Just like physics defines the optimal structure for sand, Silk helps optimize business structures. If your business needs help with AI training, automation, or figuring out how to integrate intelligent agents to really make an impact, you should check out embersilk.com.
So getting back to building, once you have that perfect 1% water ratio, what's next?
Compaction, right? You have to pack it down.
Yes. And a well-compacted structure can be up to 30% stronger. By packing the grains closer, you shorten those capillary bridges, which actually makes them even stronger.
And I found this fascinating. The best way to do it is with your hands.
That's right.
Using a little plastic spade or shovel actually creates tiny fractures and weak points in the structure. Uniform pressure from your hands is way better.
And when you get everything just right, the water ratio, the compaction, the results are just incredible. In experiments, they've built stable sand cylinders 2.5 meters tall with only a 20-centimeter radius.
That's amazing. And in theory, it could go even higher.
The theory suggests you could get up to 5 meters. 5 meters of just sand and a tiny bit of water.
5 meters,
Yeah.
It's just wild. And this isn't just for fun at the beach, is it? This has some huge real-world implications.
Oh, absolutely. These same principles are fundamental to civil engineering, to geophysics. Understanding granular cohesion is how we ensure the stability of dams, of embankments, of retaining walls.
It even helps us understand things like landslides or liquefaction in earthquakes.
It does. Your simple sandcastle is actually a micro model for how we build huge, enduring structures all over the world.
It's just such an optimistic thought. Our ability to build these incredible things from something so small to something so massive, it all comes down to just understanding and mastering these hidden forces of physics that are right in front of us.
It shows that our ingenuity is really our most powerful tool.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.